Hello and welcome to MATLAB programming for numerical computations. We are in module 3. In the first part of this module, we are doing numerical differentiation. In lecture 3.1, we considered how to compute f dash of x for a given function. In this particular module, we are going to go forward and take one example which is of a practical nature, as well as for a single variable problem, find higher derivatives. Specifically, we are just going to look at f double dash of x for a couple of example problems. So in the previous lecture, we have seen how to compute the first derivative. Now instead, if we want to compute the second derivative using central difference formula, we get f double dash of x is f of x plus h minus 2fx plus f of x minus h divided by h squared. Instead of writing x plus h, x and x minus h, I have given subscripts I plus 1, I and I minus 1. This central difference formula, just as we had seen in the previous lecture, is h to the power 2 accurate. You recall in the previous lecture, f dash of x was given as f of x I plus 1 minus f x I minus 1 whole thing divided by 2h. That was the first derivative using the central difference formula. This is the formula for the second derivative. This is the formula for the third derivative, and so on and so forth. We can compute formulae for higher derivatives. Over here, this should be h cubed and not h squared. In this lecture, we are only going to concern ourselves with the second derivative over here. So let's look at the problem again. F of x equal to tan inverse of x. And let's compute f double dash of x. Okay, let's go on to MATLAB, and we wanted to find f double dash of x at x equal to a, and a is 1. Let's say h was 1e minus 4. Okay, so we wanted to compute f double dash of tan inverse. F double dash is given by this particular formula. So true val equal to 2 multiplied by a divided by 1 plus a squared, the whole squared, negative of that. And I'll just put a negative sign. This is what our true val is. So true val is minus 0.5. Let's compute the numerical derivative using the formula given over here. That is a plus h minus 2fa plus f of a minus h divided by h squared. F is nothing but a tan. So num diff equal to a tan of a plus h minus 2 times a tan of a minus 2 times a tan of a plus a tan of a minus h. A minus h. Let's put this all in brackets divided by h squared. That's going to be our num diff, and num diff is approximately equal to minus 0.5. The error between the difference between true val and num diff is abs of true val minus num diff. Okay, and the error is of the order of 1.4 into 10 to the power minus 8. Okay, so now that we have considered f double dash of x for tan inverse of x, let's go on to the next example. This example was taken from the computational techniques course, module 6 part 2. For this, f of x was 2 minus x plus ln x. What we are going to do today is to find f dash x and f double dash x for this particular function using central derivatives. I recommend what you may probably do at this stage, if you have not already tried to solve this particular problem from the previous lecture, is perhaps you can pause this lecture and take a few minutes in order to try solving f dash of x and f double dash of x for this particular example. you may probably do it for just one value of step size h. Let's say you take h equal to 10 to the power minus 4 and try to solve this problem. Okay. Meanwhile, I'll give you the solution for this problem in MATLAB as well. Okay. I have cleared the screen. Let's say edit numdiff2 numerical differentiation for the second problem. 2 minus x plus ln x. Okay, let's say we wanted to find this at let's perhaps say that we wanted to compute this again at x at a equal to 1 and h equal to 1e minus 4. Okay, f of f1, let's say we call f of x plus h as f1, f of x equal to f2 and f of x minus h equal to f3. So that's going to be 2 minus a plus h. In fact, let's write it this way: x equal to a plus h, f1 equal to 2 minus x plus log of x. Okay, and we copy paste. Okay, x equal to a and f2 equal to this, x equal to a minus h and f3 equal to this. Trueval 1, let's call this for f dash, and that is going to be 1 by x minus 1, so 1 by a minus 1. Trueval 2 is minus 1 by a squared. Okay, so this is what we need for numerical derivatives. Numdiff1 is nothing but, so f dash of x was f1 minus f3 divided by 2h. f1 minus f3 divided by 2 multiplied by h. Numdiff2 was f1 minus 2f2 plus f3, f1 minus 2 multiplied by f2 plus f3 divided by h squared. That's our numdiff2. ERR1 equal to ABS of Trueval1 minus numdiff1. Actually, rather than saying numdiff, we will call this as numval. Okay, press shift and enter, so all the values will get changed, and numval2. So that's error 1 and ERR2 equal to ABS Trueval2 minus numval2. Okay, let's save this and run this. Okay, so we will get ERR1 is 3 into 10 to the power minus 9, ERR2 is 5 into 10 to the power minus 9. Okay, if we check numval1, that is 3 into 10 to the power minus 9, when we expect Trueval1 as 0, numval2 is minus 1, we are expecting Trueval2 also to be equal to minus 1. Okay, so as we can see that the errors using central difference formula are for h equal to 10 to the power minus 4 are fairly small. Okay, Okay, so now that we have completed the numerical differentiation for the second example, 2 minus x plus ln x, let's now head on over and look at a practical problem, a problem of practical interest. This comes from chemistry, as you all know that the rate of reaction can be written in the Arrhenius form given over here. So rate R is K multiplied by e to the power minus e by RT multiplied by concentration to the power 1.25. The rate constant K is equal to 1000 and E by R equal to 2500. Let's go on to MATLAB and try to solve this problem. And edit, reaction, rate, differentiation. R equal to K multiplied by e to the power minus e by RT multiplied by c to the power 1.25. Okay. Constants K equal to and e by R equal to. So K was 1000 and E by R is 2500. Okay. Differentiation. Do this at C equal to 1.0 and T equal to 600. Right? Okay. So now the analytical derivative for this guy. Okay. So temperature is the thing that is varying. So because it's e to the power minus e by RT, it's basically going to be e by RT squared, okay, multiplied by the rate R itself. So let's first calculate the rate R equal to K multiplied by exp minus e by R divided by T multiplied by c to the power 1.25. That's the rate. True val is just going to be equal to R multiplied by E by R divided by T squared. That's our true val. Okay. Now, then for the numerical differentiation, we want to calculate R1, and R1 is going to be nothing but K multiplied by e to the power this guy, but instead of T, we will have T plus H. Okay. So let's just copy this. Okay, and we will put T plus H over here using central difference formula. Let's copy and paste this over here, and R2 is going to be this, but it's going to be T minus H. Okay, and numval is going to be equal to nothing but R1 minus R2 divided by 2 multiplied by H. Now the question is, what is the value of H that we need to take? So H, let's just take that as we have been doing this before. Let's just take H equal to 1 multiplied by 10 to the power minus 4. Okay, and error is going to be equal to ABS true val minus num val. Let's save and run this problem, and we hope that there is no error. And this runs, and the error, that's the difference between the true val and num val, is 4 multiplied by 10 to the power minus 11. The true val is 0.1077 and num val will also look same, 0.1077. So that completes our exercise of finding dr by dt at T equal to 600 kelvins using the central difference formula, where R is the rate of chemical reaction of the Arrhenius form. What you can try to do is see the effect of other values of H, how increasing or decreasing the value of H changes the errors in dr by dt. we had seen in the previous lecture that the optimal value of h is machine precision to the power 1 by 3 for central difference formula for f dash of x. The machine precision to the power 1 by 3 is when the overall temperature, or x, the independent variable, is of the order 1. If the independent variable is of a different order, the optimal value of h changes accordingly. Prior to looking at this example, we looked at the other example 2 minus x plus ln x and computed f dash of x as well as f double dash of x. For central difference formula of f dash of x, the optimum value of h happens to be epsilon to the power 1 by 3, whereas for the second derivative central difference formula, the optimal value of h is epsilon to the power 1 by 4. This is also something that you can probably verify as a practice problem. In the next lecture, we are going to revisit this physical example of this rate of reaction. With this, I come to the end of lecture 3.2 and I will see you in the next lecture. Thank you and goodbye.